Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to discuss on the topic Direct Sequence Spread Binary PSK Systems, Signal Space Dimensionality and Processing Gain. Please note, here we will be providing the signal space dimensionality analysis of the DS-BPSK system, and at the end of it, we will derive an expression for the processing gain of the DS-BPSK system due to the use of the spread spectrum technology. Let me start this discussion with the model for the DS-BPSK system. The input to the DS-BPSK system is the binary data sequence B of t, which is fed to a binary PSK modulator that also uses a carrier, which is usually given by square root of 2 by Tb cos 2 pi fct. This modulated signal is then fed as an input to the direct sequence spreading system that uses a PN sequence given by C of t to create a spreaded signal X of t. Here, X of t is the DS-BPSK system's transmitted signal. Now coming to the channel, we will assume the channel is free of noise. However, there is an interfering signal used by the jammer to obstruct the communication. Let this signal be represented by J of t. Coming to the receiver part, the received signal is denoted by Y of t, which is then given to a D-spreading system that once again uses a locally generated PN sequence C of t to create U of t. U of t is the input to the BPSK receiver. Please note, here we will be using a coherent detector to perform demodulation. The coherent detector is also provided with a locally generated carrier, which is an exact replica of the carrier that is used in the modulator of the BPSK system. The output of this complete system is an estimate of the binary sequence B of t. Let us now write equations for each of these signals in terms of mathematical expressions. I am going to start with the binary PSK system. Let the transmitted signals of the binary PSK system be represented by S1 of t and S2 of t, which represent symbols 1 and 0 respectively. So, S1 of t here represents symbol 1 and S2 of t here represents symbol 0. Please note, this is a PSK system. So, the only change between S1 of t and S2 of t representation is the phase. If S1 of t is represented by square root of 2Eb by Tb cos 2 pi fct, then S2 of t will be represented by square root of 2Eb by Tb cos 2 pi fct plus pi, which means when you are transmitting symbol 0, you phase advance the carrier by 180 degree. Since cos 2 pi fct plus pi is equal to minus cos 2 pi fct, S2 of t gets simplified to minus square root of 2Eb by Tb cos 2 pi fct. By analyzing the RHS of equation 1 for both S1 of t and S2 of t, I can write a generic expression for the binary PSK modulated signal as S of t equals plus or minus square root of 2Eb by Tb cos 2 pi fct. Plus symbol here represents transmission of symbol 1, minus represents transmission of symbol 0. Then, as per the DS-BPSK system, S of t is given as input to the direct sequence spreading system. The output of this direct sequence spreading is X of t, and it is simply the multiplication of the input of the system, which is S of t, with the PN sequence C of t. So, DS-BPSK signal X of t is equal to S of t multiplied by C of t. Let us now move on to the receiver part. The received signal Y of t is equal to X of t, which is the transmitted signal, plus J of t, which is the interfering signal. From our previous expression, we note that X of t is equal to S of t C of t. So, I will write it here. So, the output of the channel will be Y of t equals C of t multiplied by S of t plus J of t, where S of t represents the binary PSK signal and C of t is the PN sequence. This signal, that is Y of t, is then fed to the D-spreading system that once again multiplies y of t with the locally generated Pn sequence. I will substitute equation 5 RHS in place of y of t here, and multiplying the same will get u of t as c square of t into s of t plus c of t into j of t. Please note, C of t is the Pn sequence, and we generally represent Pn sequence as either -1 or +1. That is, the chips of the Pn sequence are represented in polar format. Since we have a c square of t here, that will cause either the -1 or the +1 to become +1 itself. So, c square of t will reduce to 1, and therefore, the final expression for the d-spreaded signal is s of t plus c of t into j of t. By analyzing this expression, we note that the input to the coherent detector is a combination of the signal term s of t plus the additional component c of t multiplied by j of t, which is of quite higher frequency compared to that of s of t. The second component can be regarded as the interfering component. Right. With that brief introduction to the DS-BPSK system, let us now start the discussion on the signal space dimensionality for the DS-BPSK system. I am going to start the discussion on the DS-BPSK signal space dimensionality by considering a set of orthonormal basis functions. The first function is phi k of t and is given by square root of 2 by tc cos 2 pi fct, where t varies from ktc to k plus 1 tc and 0 otherwise. The second basis function is given by phi k tilde of t and is equal to square root of 2 by tc sin 2 pi fct, where t varies from ktc to k plus 1 tc once again and 0 otherwise. Please note, we have used tc to represent the orthonormal basis functions instead of our conventional representation of tb. Tc here is the chip duration, and each bit duration will have n number of chips. So, the variable k here will vary from 0 to n minus 1, and as I said, n itself represents the number of chips per bit. We have previously given the expression for the transmitted signal of the DS-BPSK system, which is x of t, and is given by c of t, which is our Pn sequence, multiplied with s of t, which is our BPSK modulated signal. Let us now substitute for s of t from equation 2. So, x of t becomes c of t multiplied by this term is s of t, that is the binary PSK modulated signal. I am going to now take the square root of 2EB by TB towards the constant term. So, the next term would be plus or minus square root of 2EB by TB, but TB is equal to NTC. So, here I have written in terms of NTC here. Following that, we have C of t multiplied by cos 2 pi fct. Let me now split the contents of this square root here. I will write it as plus or minus square root of EB by n followed by C of t. Then I will write the rest of the square root term, which is square root of 2 by tc cos 2 pi fct. Now, if you look at this part carefully, this is nothing but the first orthonormal basis function we have defined previously, which is equation number 7. So, in my next step, I will replace this by phi k of t. Therefore, the DS-BPSK transmitted signal x of t is given by plus or minus square root of EB by n. Then I am going to write C of t, which is the Pn sequence signal, in terms of the Pn sequence bits. So, C of t can be written as summation k varying from 0 to n minus 1 multiplied by C of k followed by phi k of t retained as it is. It should be noted that x of t is defined over 1 bit duration. Therefore, t here varies from 0 to 1 TB. As previously said, EB here represents the signal energy per bit. The positive sign corresponds to the transmission of bit 1, negative sign corresponds to the transmission of bit 0, and the sequence Ck, which is given by C0, C1, etc. till Cn minus 1, represents the Pn sequence. By analyzing the RHS of equation 9 carefully, we will find that if I expand the summation term, I will have totally n components on the RHS of equation 9. Therefore, I can now say the transmitted DS-BPSK signal x of t is n-dimensional in nature, and therefore it would require at least capital N orthonormal basis functions for representing the same. Right. That is about the signal space analysis of the DS-BPSK signal x of t. Let us now provide a signal space dimensionality for the jamming signal j of t. Usually, the jammer will place all of its available energy in the same n-dimensional signal space as that of the transmitted DS-BPSK signal x of t. This is quite evident as well, because if he places his energy elsewhere, then that energy would be wasted. Another important thing to note about the jammer is he may or may not have the complete information about the transmitted signal bandwidth. Additionally, he also may or may not have knowledge about the transmitted signal phase. Therefore, we must understand jamming a transmitted signal of DS-BPSK system is quite difficult. I am going to start the signal space dimensionality analysis of the jamming signal by representing the jamming signal j of t using the two orthonormal basis functions given in equation 7 and equation 8 here. This is given in equation 10. So, the jamming signal j of t is written as summation k varying from 0 to n minus 1 jk into phi k of t, where phi k of t is the first orthonormal basis function, plus summation k varying from 0 to n minus 1 jk tilde into phi k tilde of t, where phi k tilde is the second orthonormal basis function. Please note that both jk and jk tilde are the coefficients of the jamming signal, which can be given directly by using the second equation of the Gram-Schmidt orthogonalization. That is, jk is equal to integral 0 to tb j of t into phi k of t dt for k varying from 0 to n minus 1, and jk tilde is equal to integral 0 to tb j of t multiplied by phi k tilde of t dt for k once again varying from 0 to n minus 1. Now, by analyzing the RHS of equation 10 carefully, we find that there are totally 2n terms in the RHS of equation 10 when the summation is expanded. So, we can now say that the interference, that is j of t, is two-dimensional in nature. That is, it has twice the number of dimensions as that of the transmitted DS-BPSK signal x of t. The average power of the interference j of t is given by capital J equal to 1 divided by Tb integral 0 to Tb j square of t dt. In the RHS of this equation, we note we have j of t. So, let us substitute the j of t from equation 10 and try to expand this equation. So, I have written substitute j of t from equation 10 and simplify. I have written j of t here. This complete term is nothing but j of t. Then we have the square as well. This is in the form of a plus b whole square. So, let us expand it. The first term in the next step here is a square. Then we have b square plus 2ab. So, a is nothing but summation k varying from 1 to n minus 1 jk phi k of t. So, it will be summation k varying from 0 to n minus 1 jk square phi k square of t. And then I have the integral here, which I have taken inside the bracket. In a very similar fashion, I have written b square, which is for the second term. Then we have 2ab. Though we have summation appearing twice here, since the limits of summation are the same, it is okay to have just one summation retained. So, this will be 2 multiplied by summation k varying from 0 to n minus 1 jk into jk tilde multiplied by integral 0 to tb phi k of t multiplied by phi k tilde of t. In my next step here, I am going to separate the continuous terms from the discontinuous terms. That is, jk in the first step here is a coefficient. So, I will take it outside the integral, and the integral appears only for phi k square of t. The same is done for the second term as well. Coming to the last term, we look at this particular part. What do we have here? Integral 0 to tb phi k of t into phi k tilde of t dt. We know that phi k of t as well as phi k tilde of t are the orthonormal basis functions. Therefore, this integration will result in S0. This is the third equation taken from the Gram-Schmidt orthogonality procedure. I have put that 0 here. Coming to the next term here, look at this particular term. This is integration 0 to Tb phi k square of t dt. This is nothing but the energy of the signal phi k of t. Now, since phi k of t is an orthonormal basis function, it will have unit energy. That is why in my next step, I will replace the integral term with plus 1. The same is done again for the second integral term in the second here. So, it is once again plus 1. Therefore, the average power of the jamming signal capital J is given by 1 divided by Tb summation k varying from 0 to n minus 1 jk square plus 1 divided by Tb summation k varying from 0 to n minus 1 jk tilde square. Now, very importantly, since the jammer does not have complete knowledge on the signal phase of the transmitted signal, what he commonly does is he will distribute energy equally among both Jk as well as Jk tilde. Therefore, I can now assume them to be equal. So, in my next step, I am going to say summation k varying from 0 to n minus 1 Jk square is equal to summation k varying from 0 to n minus 1 Jk tilde square. Please note, this is because the jammer does not have the knowledge of the transmitted signal phase. Let us now substitute equation 14 back into equation 13. Since the RHS of equation 13 is the same in both the first as well as the second term, the average power of the interfering signal J is equal to 2 divided by Tb summation k varying from 0 to n minus 1 Jk square. Right. With that, now we have analyzed the signal space dimensionality of the interfering signal as well. Let us now move on to the receiver part. Please note, the overall idea here is to tie all of these results what we have been finding and tie them together to find the signal to noise ratios measured at the input and output of the DS-BPSK receiver. Right, let us start with the dimensionality analysis of the receiver. Please note, I am going to start my analysis by writing an expression for the output of the coherent detector at the receiver part of the DS-BPSK system. Let that output be represented by V of t. Please note, this is just before the sampler that is in the coherent detector. This is the expression for V of t. The output of this receiver, it should be noted, is equal to integral 0 to Tb, the input of the receiver, which is u of t, multiplied by the basis function phi of t. The basis function phi of t is given by square root of 2 divided by Tb cos 2 pi fct. If you analyze the RHS of this equation, you will find we have written exactly the same. So, we have integral 0 to Tb, the input of the receiver u of t multiplied by the basis function, which is square root of 2 by Tb multiplied by cos 2 pi fct, and then we have the dt. Now, since u of t is a combination of the signal component as well as the noise component, particularly the interference component, I can write the receiver output V as Vs plus Vcj, where Vs is due to the despreaded binary PSK signal S of t, and the second component is due to the spreading interference caused by C of t multiplied with J of t. These two components are given in equation 17 and 18 here. So, Vs is equal to square root of 2 by Tb integral 0 to Tb S of t multiplied by cos 2 pi fct dt, and Vcj is equal to square root of 2 by Tb integral 0 to Tb C of t multiplied with J of t then cos 2 pi fct dt. The first equation is the signal part here, and the second equation is the interference part. Let us now first analyze the signal space dimensionality of the first part, which is V of S. The RHS of the equation 17 has S of t, which is our binary PSK modulated signal. We already have given an expression for the same, and it is rewritten here as S of t equals plus or minus 2EB by TB cos 2 pi FCT for t varying from 0 to TB. By assuming that the carrier frequency Fc is an integer multiple of 1 divided by Tb, we will have Vs, which is a signal component, as plus or minus root Tb. Further, the peak instantaneous power of this signal can be given as Ps equal to 1 divided by Tb integral 0 to Tb S square of t dt, which is nothing but the energy of the signal denoted by Eb. Let us now move on to the second component, which is Vcj. Please note the second component has a C of t term, which is our Pn sequence. Now I am going to write C of t in terms of its chips as C of t equals summation k varying from 0 to n minus 1 Ck. So Vcj now becomes square root of 2 by Tb. Then we have C of t replaced by summation k varying from 0 to n minus 1 Ck. And now since we have written everything in terms of the chips, the integral limits also change for one chip duration, that is from ktc to k plus 1 tc. Then we have the rest of the equation as it is, that is j of t multiplied by cos 2 pi fct dt. Let me now rearrange this equation. I am going to now rewrite Tb as ntc because 1 Tb is equals to ntc. And in my next step, I am going to rearrange it once again by taking square root of 2 by Tc to this part, and I am going to tie it with the cos 2 pi fct part. And the rest of the equation will be retained as it is in this step. Now, if you look at this part here that is shown in the square bracket, you will know this is nothing but phi k of t. So, that is what is written here. Also, in the same step, I have made a few more modifications. We know that n is equal to Tb divided by Tc. So, this n here is replaced with Tc divided by Tb. Also, I will be changing the integration limits from Tc to Tb. So, it would be integral 0 to Tb. Now, if you analyze this part carefully, you will note that it is nothing but the second equation of the Gram-Schmidt, that is for the signal coefficient. So, this complete term reduces to Jk, and this is written here. Therefore, we can now write the interference component Vcj as square root of Tc by Tb summation k varying from 0 to n minus 1 Ck into Jk. Now, we will assume that the Pn sequence generated is an independent, identically distributed binary sequence. So, I can now write this equation, which is written in terms of the sample values, as capital Vcj equals square root of Tc by Tb summation k varying from 0 to n minus 1 capital Ck followed by capital Jk. Please note that Vcj and Ck represent the random variables with sample values Vcj and Ck, which were shown in equation 22 previously. Further, in the equation 23 here, let us assume the jammer is fixed. So, since we have already assumed that Ck is treated as an independent, identically distributed random variable, the probability of the event Ck either being equal to plus 1 or equal to minus 1 will be the same. That is, probability of Ck equals to plus 1 is equal to probability of Ck equals to minus 1, which will cause these values to be equal to 1 by 2. Let us now find the mean of the variable Vcj. So, it is expectation of Ck into Jk given Jk is equal to Jk multiplied by probability of Ck equals to 1 minus of Jk multiplied by probability of Ck equals to minus 1. I will retain Jk as it is in both these terms, but I will substitute for P of Ck equals to 1 and minus 1, which are both 1 by 2. Therefore, the mean value of the variable Vcj is 0. This is also specified here. Let me now analyze the variance of the variable Vcj here. For a fixed vector j representing the set of coefficients j0, j1 till jn minus 1, the variance of Vcj is given by jtc divided by 2. Therefore, we can now finally say the random variable Vcj has a mean equal to 0 and a variance equal to jtc divided by 2. With that, we can now finally proceed to write an expression for the signal to noise ratio at the output and input of the DS-BPSK receiver. I'm going to start with the signal to noise ratio at the output. Generally, the expression for signal to noise ratio is the signal power divided by the noise power. Let the signal power be represented as PS and the noise power is nothing but the variance of the variable VCJ given J. We have previously found the signal power to be equal to EB. This is taken from equation 20 and the variance of the noise component is equal to JTC divided by 2, which was our previous equation, that is 26. Rearranging this, we will find the signal to noise ratio at the output of the DS-BPSK receiver to be 2EB divided by JTC. In a very similar fashion, let me now write an expression for the signal to noise ratio at the input of the receiver. This is given here. So, signal to noise ratio at the input of the receiver is equal to signal power divided by the noise power. The signal power at the input of the receiver is given by EB divided by TB and the average noise power is represented by J, and this is already analyzed in equation 15. In my next step, I am going to compare the signal to noise ratios at the output as well as at the input of the DS-BPSK receiver. This is shown in equation 29 here. After substituting for all the values and simplifying, we find the signal to noise ratio at the output of the DS-BPSK receiver is equal to 2 TB divided by TC multiplied by signal to noise ratio at the input of the same. Please note, this is given in terms of power. However, it is quite customary to express the signal to noise ratios in terms of decibels. So, I will be now rewriting equation 29 in terms of decibels. So, it would be 10 log 10 of SNR output is equal to, I am going to take this part first. So, it would be 10 log 10 of SNR input. Then I am going to take this 2 here. So, 10 log 10 of 2, please make that correction. And lastly, I am going to take TB by TC. So, it would be 10 log 10 of TB by TC. Let me simplify this. The first term is retained as it is, no change. 10 log 10 of 2 is equal to 3. And in the last term, I am going to write TB by TC as PG, where PG represents the processing gain. Please note the equation for PG is given here. It should be noted the 3 dB term in the RHS of equation 30 accounts for the gain in the signal to noise ratio obtained because of the use of the coherent detection. Please remember, we have used coherent detection for performing BPSK demodulation. However, this term is not of much importance to us because we are trying to analyze a spread spectrum system. So, what is more important to us here is the third term that defines the processing gain. This term accounts for the gain in the signal to noise ratio obtained due to the use of the spread spectrum technique. Specifically, this last term represents the gain that is achieved by performing spreading operation of the output of the modulator. Coming to the processing gain, which is the ratio of the bit duration to the chip duration, we will note that if I want to increase the signal to noise ratio of the DS-BPSK system, then I have to either make the PN sequence longer because TB by TC is nothing but N, or I have to make the chip duration, which is TC, smaller. By performing any of these two operations, we will create a higher value of signal to noise ratio for the DS-BPSK system. Right. That is about the analysis of signal space dimensionality and finding an expression for the processing gain of a DS-BPSK system. Lastly, before I end this video, I would also like to provide some information on expressing PG in terms of other variables. We note that the rate of transmission, that is RB, is 1 divided by TB. So, I can write TB as 1 divided by RB then. Also, the bandwidth of the PN sequence C of t is related to the chip duration by WC equals 1 divided by TC. So, I can write TC as 1 divided by WC. We have previously said that processing gain is the ratio of bit duration divided by chip duration. Now, I'll be replacing TB and TC in the equation for processing gain and write the same in terms of RB and WC. As shown in equation 32 here, TB is equals to 1 divided by RB, and as shown in equation 33, TC is equals to 1 divided by WC. Rewriting this, we will obtain the processing gain as WC divided by RB. This is just an alternative expression for the processing gain written in terms of TB and TC. Right. With that, we have come to the end of this video. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.